Hi guys, welcome to chemistry lesson 4.01, part one. This is going to be a two-part video over the electromagnetic spectrum. And this looks like a pretty big departure from what we've been doing. We've been talking about moles and atoms and isotopes. So why all of a sudden do we have a diagram of waves here and light? And what's all this about? Well, the other thing we could call this is called the electromagnetic spectrum. We could also call it the spectrum of electromagnetic radiation. Spectrum of electromagnetic radiation. And it turns out that in order to understand atoms, and especially electrons, we have to know what electromagnetic radiation is and how it operates. You and I communicate through sound. We use our voices. Atoms don't have voice boxes. So the way that we can learn about atoms and the particles in atoms is to understand how they, in a sense, communicate, and I'm using air quotes here. They take in and give off electromagnetic radiation. Well, if we don't understand what that is, it's going to be difficult to discuss it. So the electromagnetic spectrum ranges from radio waves to microwaves. We've got infrared, visible, UV, X-ray, and gamma ray. So let's talk about these kind of in turn. You'll see the same labels down here at the bottom. And look at this little tiny rainbow right in the middle. What they've done is they've taken that and they have expanded it here. So we can see that, so this is an expansion. They took that and they just expanded it. Well, the different parts of the spectrum are used for different things. So obviously visible light here in the middle, we predominantly are aware of it because it's what our eyes use. The electromagnetic radiation in these wavelengths excite chemical receptors in our eyes and allow us to see. We also have things like some of these are used for photosynthesis. So really, this is the ranges that deal with living things. Radio waves, if you're listening to AM, FM radio, that exists down here. So now we're on this main bar and this main bar. Those exist here. Microwaves, you probably are thinking of your microwave at home, but the microwave applications are very, very diverse. All of our cell phones, all of our TV exist in this. In fact, there are auctions. They'll actually auction off entire sections of the electromagnetic spectrum. People pay for the right to use what we're going to learn are called wavelengths. We don't have a definition for that yet. Infrared. You might have seen these if you go to a hotel. There's an infrared lamp in the ceiling. You turn it on and it releases heat. And it looks to our eyes red because it's next to this part of the visible light. So infrared, infra means below. It's below red. So infrared is below the red portion of visible light. Ultraviolet, ultra means above, and that's above the purple. So we've got purple here at the other end of the visible light spectrum. And you guys know this is UV. You know, if you go out in the sun too long and you get too many UV rays, it'll give you a sunburn. But you could stand underneath a heat lamp all day. It's not going to do a thing to you except keep you nice and toasty warm. So we obviously have things are changing as we move up this electromagnetic spectrum. And when we get to X-rays, now you know we're definitely changing, because when you go in to get an X-ray, they cover up anything not being X-rayed with a layer of lead. Well, why do they do that? It's bad for you. It can make you really, really sick. Marie Curie, who won the Nobel Prize in, I don't know if it was physics or chemistry or both, did tons of research in this part of the electromagnetic spectrum. Before her, we really didn't know all that much about it, but a lot of the natural elements she worked with gave off X-rays and gamma rays, and she developed cancer. She died. So this can make you very sick. Gamma rays, you really don't even get the chance to get cancer. Gamma rays, contrary to what the comic books tell you, you don't turn into the Incredible Hulk if you get zapped by gamma rays. You just die. This is what killed the survivors. The people who were at Hiroshima and Nagasaki were exposed to lethal doses of gamma radiation, and they died of radiation poisoning. So you can't survive. So this, if we're thinking about survivability, why? What's going on here? Well, we can talk about this in terms of energy. So we can say down here we have very low energy. We can say up here we have very high energy. And there's a formula we can use for that. We're not going to worry about that so much. But how does that relate to this? I keep pointing to this, and you see this wave, and it's really long and spread out. And as we get closer to the gamma end, it starts moving much faster. And at the end, you can barely even see the distance between the tops of two waves. Well, that distance is what we call wavelength. So the first thing that we need to talk about is wavelength. So wavelength is the distance between two wave crests or troughs. Two wave crests or troughs. These are crests. So I've got a crest here, I've got a trough here, I've got a crest here, I've got a trough here. And so this distance here would be one wavelength. Or we could look at that as one wavelength. Because we're talking about distance, the unit is a meter. Now, sometimes you'll see down here, do you see nm? That's nanometer, nm. So this would be 400. Let me do let me actually do them in their colors. So 700 nanometers would be 700 times 10 to the minus 9th meters. Is that right? Correct scientific notation? No, but it proves my point. The symbol for wavelength, so it's got a funky symbol, is the Greek letter lambda. And that's always the symbol for wavelength. So you'll notice as I go up, my wavelength becomes shorter. I could also say smaller. Down here at this end of the spectrum, I have longer or larger wavelengths. So my number here is going to be much smaller. And you can see this is actually 10 to the minus 13th. And this is 10 to the second. So down here in the radio waves, we have wavelengths that are the length of a football field. And up here, I have wavelengths that are the width of an atomic nucleus. So these are huge. Remember, these are exponential orders of magnitude. Well, what can we say about energy and wavelength? What's our relationship? Try to answer it. If you need to, pause the video. Okay, for the answer, did you say they're indirectly proportional? So energy and wavelength, that's wavelength, are inversely, inversely proportional. Lower the energy, the higher the energy, the smaller the wavelength, the lower the energy, the longer the wavelength, the larger the wavelength. So we have an inverse proportional. So if I asked you to put the following, and I will on the test, if I gave you X-ray, infrared, or gamma and microwave, and I said, put these in order of increasing energy or put these in order of decreasing wavelength, you need to be able to answer that question on the test. And we'll practice doing that in class. All right, that gives us an introduction. We talked about, so our takeaways here are, why are we talking about this? It's because atoms absorb and release electromagnetic radiation all the time. We divide it into regions, which you do need to know. The radio wave is the lower energy and the gamma ray is the higher energy. And, oh, you know what? I want to talk about, well, let's say frequency. I'll say frequency for the next video. And we talked about wavelength, the distance between two waves, between two crests or two troughs. So we're going to go on in part 2 to talk about frequency and how frequency is related to both wavelength and energy. All right, that's part 1. Thanks for watching.